Hi, this is Arzu Naim. My student number is 46218858, and I have selected the topic graph pattern matching and networking data. So I believe the task of searching for patterns in graph structured data has applications in such big areas such as computer vision, biology, computer designs, social network, and there are many more other areas where we can use graph pattern matching. But graph-based pattern matching is not a single problem, but it is a set of related problems. So these range from the NP-complete isomorphism problem, in which matches are based strictly on graph structure. And my report is basically focused on the subgraph isomorphism and NP isomorphism features. Starting with the introduction part, so the process of finding particular patterns within a graph data structure is known as graph pattern matching, as I told earlier as well. And I did some background digging about the isomorphism feature, and I find out that the subgraph isomorphism is a one-to-one mapping between the vertices and edges of the target graph, and the subset of the vertices and edges of the pattern graph, which maintain a relationship between the vertices and edges. So I have used a figure here, just this is a very common figure which I've used here, and where the subgraph isomorphism is known to be as NP complete. And it is like impractical to solve subgraph isomorphism directly in large graphs. So this leaves us with like two options for matching patterns in reasonable time. So one is use an approximate isomorphism algorithm, and which may or may not yield like optimal solution, but still we can use it. And the second one is use an exact isomorphism algorithm, but we can only apply it to a subset of the main data set. So moving ahead, like in this diagram, subgraph isomorphism is used to describe graph pattern matching, which states that the presence or absence of a subgraph that is isomorphic to a given pattern in a given data graph implies that GP contains GD. So this is like a graph, and we have just this is a subgraph of it, but we can say that these both graphs is, I mean, this GT is a subgraph of GP. So moving ahead on motivation part, I've used a figure here where the isomorphism of a graph is not the same as graph matching. Matching is a specific subgraph of a graph, whereas graph isomorphism checks if two graphs are same or not. But this is a NP subset to match the same colored graph. So we are just focusing on the same colored lines, dots here. And NP is a set of decision problems that can be solved by a non-deterministic Turing machine, like in any polynomial time. So according to the diagram, we can see that subgraph isomorphism is used to identify molecules with similar structure. And like we can say in image recognition. So we can identify the objects and images in social network analysis, where it is used to identify communities of similar users and with similar behavior patterns. So I did some digging in it and I found some related work. Yeah. So according this figure is basically a case study in pattern matching, and the input graph various vertices are identified by numerical letters like A, B, C, D, E, and the pattern various vertices are identified by capital letters. And here the numbers are like enclosed in square brackets like these ones. These are one-to-one correspondence, like this indicate a bijective function, we can say in simpler words. So here in figure, so V and E are vertices and uh, vertex and edges. And I have included a methodology for the same. Yeah. So according to my understanding, what I believe when I went through the multiple research paper, I believe that GraphPy is a novel four-component high-performance distributed pattern matching system. So in this work, in this GraphPy thing, it is very fast and scalable group pattern matching system. And according to this figure as well. Yeah. The overall architecture of GraphPy, this is the overall architecture, and it mainly explores how to select a better schedule and a set of restrictions through the information that is provided by the input pattern and the data graph to accelerate the pattern matching process. So basically, GraphPy contains of four main things. The first one is configuration generation, performance prediction, then code generation, and then we just check whether this pattern pattern is matching or not. So in order to eliminate all redundant computation caused by automorphisms, different set of restrictions and input pattern are generated by a restriction generator. So the methodology, yeah, this is the proposed method, which I already told that it is a quick and scalable graph pattern matching that we develop. This is the overall structure for the same. What we are doing here, we are restricting. Okay, what happened? Yeah, just share my screen. Yeah, it's recording. So yeah, and the restrictions set generator is this one, and we schedule time for it, and then we see the performance model, and we use C++ code, and we execute the whole scenario, and then we check whether it is the pattern is matching or not. Then this is the algorithm which I used for the graph for the basically for GraphPy. So here this is a two-cycle based automorphism elimination algorithm, and it takes like an arbitrary pattern as inputs and outputs, multiple sets of restrictions, and each of them can eliminate all redundant computation. So here in line 2 and 3, we are trying to generate the permutations, like we are trying to generate the automorphisms and the corresponding permutation group. uh, yeah, and then later on we are trying to run the recursive function. I think, yeah, in line 4 we are trying to kind of recursive function, trying to generate recursive function. So why we are trying to do that is, if there are permutations other than any identity permutation in the group, more restrictions need to be added to eliminate them all. So uh, for that process, we are including a condition here so that we can check whether there are permutation whether there are other permutations as well which we need to remove. For each permutation in the group, if we succeed in finding a two-cycle permutation, so we append a partial order, and then we use a set of restrictions to eliminate permutations. So we perform the cycle according to this one, and assuming that the pattern has n vertices, we run a pattern matching algorithm with the input set of restrictions and on an n vertex complete graph, and then we rerun it without restrictions. So this is basically the algorithm which I've used for my report. And conclusion part is like, I believe that GraphPy is an elite presentation conveyed design matching framework, and to eliminate the redundancy and pattern matching, we can get an accurate performance model and automorphism elimination algorithm based on two cycles. That was this one. Future work is, I believe there are still some work left which we can cover in future. Like for example, I'm so sorry, my net is a little bit off today. Yeah. So I believe query preserving compression for subgraph isomorphism based matching is like still under investigation, and we can do a little more work on that, as well as the lower bounds of graph pattern matching can still be improved using, for instance, bounded and strong stimulation. But still, the graph zero thing, the graph by thing is a good one, but there are some future work need to be done. We can work on it in the future time. These are the references which I used for my report. And here I'll paste my video presentation URL. That's a YouTube link. And I'll, yeah, I'll submit it. Thank you for the time. And yeah, sorry for the internet disturbance. Thank you.